All right, so I want to talk about graphs today. I want to talk about rates of change. This is like the third time I've had to do this video because I keep messing up one thing or another, and I probably messed up another thing right now. So you can hear the tone in my voice that um, I am frustrated. It may feel like I'm frustrated at you, but I'm frustrated at myself, and I'm going to hopefully spare you some time that I wasted in the other videos. Um, This graph is about how much did they miss you relative to the time they were gone. It's comparing dogs and cats. Really, the only thing I wanted to say with this graph is that in up until now in math classes, mostly what we're looking at is kind of like the value. Like I might say, after 5 weeks, which animal misses you more? And you say, oh my goodness, it looks like dogs do. But now going forward with calculus, what we're looking at is rates of change, is slope. Okay, so with slope, we're the question is more likely going to be which animal misses you more over time, the dog or cat. And you can tell with the slope is steeper and the amount it changes is more. So I think what this graph maker was trying to say is that the the rate of change, like the quickness with which a dog forgets you, is more than a cat. I think this is when it doesn't really hit home for me because I don't have a dog or a cat, but it does bring me to my next graph, which you'll probably need a second to process. And then usually this is a difficult thing as a presenter is actually giving your audience enough time to process it because a lot of times you're just like waiting there awkwardly and people can't process things when you're talking to them. But oftentimes I think the graphs that you put up there, you're like, this is going to blow their mind. And then they don't. And I think that's a little bit of a window into the human mind. Another window into the human mind is through social media. Um, I picked this up. I just looked up like 10 fun graphs and I picked three of them off there. This one, I was like, okay, this is something I can speak on because I like Facebook a little bit. I like Instagram. I'm not like a huge social media person, but what I really don't like is how simple people view it. Like I think there's people my age that like have this view that everything that's wrong with the world is because of social media, and they can't acknowledge all the good things that social media has created, all the ways that it's given voice to people who were formerly excluded from conversations, and I appreciate that. But what I don't think we do, I think we lose where you all suffer in the complexity is that we don't directly tell you that social media is addictive. It functions like a drug. Like your brain literally releases the same types of endorphins when you hit that like button as certain types of drugs stimulate your brain to produce. Um, and in that sense, I think that awareness is empowerment, and you all need to know that um, you need to be mindful of how you use social media, and that if you're not careful, you are going to be, and maybe, after this point in the year, probably a lot of people already are, but you need to wean yourself off of your need from being liked through social media. That would be my advice. All right, here's another one. I like this one. It's a graph of distance from plate changing over time. I'm playing it at 2x. These are a set of graphing stories. This took a whole day to do these, but we don't have that much time. This is a person running around the bases. I used to play baseball. I would run around the bases much slower than him, and I almost never had to run all the way around the bases. But when we're watching this, this is at half speed, but played at twice speed. So I believe that's regular speed. You want to be thinking at what rate is his distance from home plate changing as he circles those bases, and you might be making a mental picture of it. And just before I play the answer, think of what that graph is going to look like. I'm not going to give you that much time to process it, but um, I would bet that not many of you had the exact representation of this graph in your head. And um, all I'll say about this graph is that his rate doesn't change. He's running at the same speed for the entire graph. What changes is his relationship with home plate, I guess. When he's running from home to first, he's running directly away from home plate. When he's running from third home, he's running directly toward it. When he's running from first to second, he's not running directly away from home plate. So even though he doesn't slow down, his slope changes. So his average rate of change from home to first is more than his average rate of change from first to second. And I just want us to be thinking of what's this concept of rate of change mean in an applied context, because this is what often happens at this point is now that we've seen one or two limited applications, you're going to see like 1,000 times where it's stripped of its context, and we're going to be talking about average rate of change. And so what is average rate of change? Well, I'm going to have a graph, and I'm going to have some curve, and I'm going to use some line to approximate it. And what would I do to approximate it? Well, what we've typically seen are these triangles where this measures delta x and this is delta y. Let's make it rainbow colored. And what you've seen in past classes, delta y over delta x is equal to f of b minus f of a over b minus a. And that's a useful formula. It goes back to Algebra 1. We use the letter M to represent it, and it comes up all over the place when you go to calculus. Now, there's one thing that starts to change, and I guess what I want to do is draw another one, and I'm going to call this A, and I'm going to call this A plus H. Actually, let's call this X, and let's call this X plus H. And this is f of x, and this is f of x plus h. And I'll draw the same type of curve. I'll use a rainbow marker again. And it's the same picture, but the difference is now this space between these 2 points is defined as h. And so we could think of what's this going to look like with our new form of notation? Well, it's going to be f of x plus h minus f of x divided by h. And so what I want you to know, you're going to see h a lot. We're at that point. You see more letters than you see in numbers in your math classes. You can complain about it, but it's not going to do anything. You are a fish in water, and you just have to surrender to the flow. But what I want you to know where this is going is that we're not actually looking for an average rate of change. By the way, this is the average rate of change. Okay, we're using the average rate of change between x and x plus h to get us to this concept. And the concept is, what's the instantaneous rate of change? The instantaneous rate of change is, I'll go back to non-rainbow to make it clear that I'm trying to make a real point here. The instantaneous rate of change is what's that slope of the tangent line that hits that curve at one point, and that one point is x. What is it? Well, I don't know. So I might just pick an h and approximate it. And then be like, well, but could you do better? And then you might be like, well, okay, I could pick a point that's a little bit closer. And then I could say to you, well, that's okay, but it's not exactly that black line. Could you do better? And you might say, geez, I wish you would stop asking me that, but yes, I can. And you do a little bit better. Each time you do a little bit better, and it's hard to represent any line that's closer, but I'm just trying to drive home the concept here. And the concept is that the instantaneous rate of change, which we call IROC, instantaneous rate of change. IROC used to be a car that people would drive around in the 80s. People would have long hair on the back of their head and short hair on the top, and they would drive IROC Zs. And now it's morphed into a concept in high school math classes that symbolizes instantaneous rate of change. And that instantaneous rate of change is the same formula that I had above. However, it has a limit statement, and it's the limit as h goes to 0. So the concept of this is that we're looking for the instantaneous rate of change. We're looking for what happens as this h value gets infinitesimally small? What's the slope of that tangent line? And these are things that aren't going to make sense completely the first time you watch them, but it is where we're going in course 2 and in calculus as well.